Hi everyone, this is Arash from the Existential Robotics Lab at the UC San Diego. Today I'm presenting our paper titled Riemannian Optimization for Active Mapping with Robot Teams. A fundamental prerequisite for safe and successful robot operation is the ability to explore an unknown environment and locate objects of interest for task execution. Thanks to the availability of powerful onboard computers, a single robot can nowadays perform fully autonomous exploration and mapping of an unknown environment. However, time-critical and large-scale applications, such as search and rescue, surveillance, or environment monitoring, might require a team of coordinating robots to carry out the mission. Centralized architectures, distributed linear-Gaussian models, and learning-based approaches are the most common families of solutions for multi-robot exploration. In this work, we propose a general distributed Riemannian optimization method that can be applied to the problem of distributed 3D semantic octree mapping as well as distributed SE3 planning for exploration. The combination of distributed mapping and distributed planning provides a framework for decentralized multi-robot exploration of an unknown environment. Consider a network of robots represented by an undirected graph. The goal is to collaboratively explore an unknown environment using a team of robots, each equipped with onboard sensing and processing hardware. There is no central estimation and control node, but peer-to-peer communication can be utilized for sending and receiving local maps and plans across the robot team. We decompose the problem of distributed multi-robot exploration into distributed mapping and distributed planning problems. In distributed mapping, the goal is to construct a globally consistent common 3D semantic map of the environment, given local semantically annotated point clouds. This can be formulated as distributed maximization of observation log likelihood, subject to a consensus constraint. For distributed planning, we aim to find the SE3 team trajectory that maximizes the information of the future observations and safety of the path, given the global common map computed from the distributed mapping. This can be formulated as distributed maximization of a differentiable collision and perception over objective function subject to a consensus constraint. We propose a general distributed Riemannian optimization framework that interleaves local objective function optimization with consensus updates in an iterative way. The problems of distributed mapping and distributed planning can both be formulated at specific realizations of this Riemannian optimization, where the domain manifold is the space of probability distributions and SE3 trajectories, respectively. We carry out simulated experiments in a photorealistic 3D environment powered by the Unity engine. The environment resembles an outdoor village area with various types of terrain and object classes, such as grass, asphalt, buildings, and cars. Our simulated experiments utilize 6 robots, each equipped with an RGB-D sensor. On the top, you can see the RGB-D input from each robot's perspective. The displayed 3D map is the globally consistent common semantic octomap, which is computed online using our distributed mapping method. Note that the global map can be accessed via query from any of the robots, eliminating the need for a central estimation unit. Additionally, we deployed our proposed distributed exploration method on a team of ground robots to achieve autonomous exploration and mapping of an unknown real-world indoor area. The robot team was comprised of 2 ClearPath Jackal robots and an F-110 race car robot. Our robots are equipped with an RGB-D camera where the sensor measurements are used to perform pixel classification and combined with the depth input are provided as local observations to build semantic octree maps. The communication is handled via a Wi-Fi network and multi-master ROS architecture, such that each robot runs its own ROS master. It is noteworthy that all the mapping and planning computations were carried out using the onboard robot computers with real-time performance. Thank you for watching my presentation. Please visit the paper's website for the main text and the open source implementation of our method.